Hello. By now we have seen that electricity and magnetism are not quite as separate phenomena as we have initially thought. They can relate to one another when we considered the different reference frames of different observers. We have seen that what shows up as a magnetic field in one frame of reference can be perceived as an electric field in another frame of reference. Of course, both leading to consistent descriptions of the forces acting on charges from any inertial reference frame. So let's explore this unification of electric field and magnetic field into an electromagnetic field a little bit further. To do that, let's review what the field laws are so far. We've started out with Gauss's law that either as a name for the concept of electric flux or as the definition of it, the flux of the electric field through a surface, through in particular a closed surface, relates to the charge that's enclosed inside that volume. So if here we have a cutaway view of that two-dimensional surface in three-dimensional space enclosing a charge, then we see that every field line radiating out from that charge is going to have to cross through the surface, and so the net charge inside the enclosed space is proportional to the flux of the electric field through that surface. Or in other words, the electric field is caused by electric charges. So that was Gauss's law. We haven't talked about it much, but there's a version of Gauss's law for the magnetic field that looks very similar. So instead of electric, we now deal with the magnetic flux. Definition is equivalent, just a B instead of an E in here. But the difference between magnetism and the electric equivalent is that there are no magnetic charges. If we cut a bar magnet, we don't get a separate north and south pole, but two smaller bar magnets, each still with a north and south pole. So there are no free magnetic charges, there are no magnetic monopoles, only dipoles with a dipole field and so on. And the magnetic field lines are all always closed, not starting at a free charge because there isn't a free magnetic charge. So a magnetic field line being closed can either not cross through the Gaussian surface at all, or if it does cross through, then it's crossing outward once and inward once at a different place. So either case, it gives a net contribution of 0 to the flux through the surface. Once outward and once inward is 0, always inward is still 0. If we have a oddly shaped Gaussian surface, we can pass in and out multiple times, but we'll always, with a closed loop, pass outward as many times as we pass inward. And so the flux is 0, stating that there are no magnetic charges equivalent to the free electric charges, electrons, protons, and so on. So there is a symmetry between the two Gauss's laws. That symmetry is broken a bit. Instead of a charge we have 0 here, but what breaks the symmetry is the absence of magnetic charges. Other than that, we really have a symmetry for Gauss's laws. Alright, so that's Gauss's laws. Let's look at Faraday's law next. We still have this weird little integral sign with the circle on it, reminding us that it's a closed path or surface, but it's no longer integrating over an area, no longer integrating over a closed surface, but now we are integrating along a line, along a closed line, a path integral of the electric field along a closed path, along a closed loop, and that's going to enclose an area, and through that area we can have a magnetic flux, and the change of that magnetic flux with respect to time is going to give us the path integral around the boundary. That's Faraday's law, and we've used it extensively in the past. So an electric field can be created by a changing magnetic field. That's what Faraday's law says. And there is something equivalent to it where we replace the E with B. That's Ampere's law, and we've used that extensively as well. So the line integral around the closed curve of the magnetic field along the closed curve, that's going to be proportional to the net current through that area enclosed by the curve. So there's one current and another current. We add them, each taking the sign into account. If our orientation for the curve is, for example, this way around, then by the right-hand rule we would have a positive direction as indicated here, and so the net current here would be I1 minus I2, and that's giving us the integrated magnetic field along that curve. Alright, we've used Ampere's law to calculate, for example, the magnetic field inside the solenoid and so on, and so that's come in very handy as well. But there isn't as much symmetry here between Ampere's law and Faraday's law. We have a current on the right hand side here, whereas for Faraday's law we had the change of magnetic flux to give us the similar looking left hand side, the field integrated along a closed curve. So alright, well, maybe there's something we can do to make it look a little bit more symmetric. We'll get to that. Let's first look at if there's any issues with Ampere's law. So we have a curve in three-dimensional space, and that's going to be a boundary of a surface, but that surface is not uniquely defined. For Gauss's law, if we have a boundary, a two-dimensional boundary in three-dimensional space, that uniquely selects a volume of the three-dimensional space. There isn't any ambiguity about the volume inside or outside the Gaussian surface. But for a closed curve, we can have multiple surfaces that all are bound by that same curve. Two of them are shown here, the flat circle, surface 1, and this bulged out surface 2. Now Ampere's law, of course, the left hand side, the integral around the curve, is the same for both of these surfaces because it's exactly the same curve, being the boundary of both of those surfaces. So then the right hand side must be the same also, no matter if we consider surface 1 or surface 2. And that appears to be working. We have a current going through the one surface and the other surface, so that's good. Well, we can also have current going through one surface and not through the other surface, but we can't just have the wire end here. If the wire was to end here, there couldn't be a current flowing in it. So with the wire having to continue, the only possible way to not cross through S2 is to cross back out through S1, and so we have a net zero current through S1 and also a net zero current through S2, and again we don't see a problem with Ampere's law. But there is one other case we can consider. Let's look at the similar curve represented with the two dots here in a cutaway view, and our same two surfaces S1, the flat circle represented by this line in a side view, and the other surface S2. Well, now let's have S2 go around the capacitor plate, and of course after a long time the capacitor is charged, there's going to be zero current in the physical wire, zero current through S1, zero current through S2, so after a long time there's no issue. But as the capacitor is charging, at least for a brief moment, clearly there has to be a current flowing to get the charge onto the capacitor, and so there's a current flowing through S1, but there's nothing, no physical current going through S2. So how can we save Ampere's law? Something clearly is going on here. There is a current through S1 but not through S2, so Ampere's law is either wrong or incomplete. Well, it's been successful for us so far, so we shouldn't just completely throw it out. We should see how we can modify it to maybe add something to it to make it work in this situation we haven't previously considered, without breaking it in those situations where it has already been useful to us. And so the symmetry between Ampere's and Faraday's law that we would like to get gives us a hint, but we can also just well, look at it and demand that whatever is going on in this gap, it has to somehow be equivalent to what's happening with the moving charges here. And so, well, what is happening in that gap? We of course get an electric field increasing as we are moving charges onto the capacitor plate. In fact, we have derived what the field is, close to an infinite charge of a plane of charge density Q over A, and we used Gauss's law to do that many chapters back, and then found the electric field between two capacitor plates in a parallel plate capacitor, and it just had this constant of 1 over epsilon naught Q over A, and so Q increases because of the current flowing. dQ by dt is just the current. Well, the electric field is Q over epsilon naught A, but the electric flux is Z times the area. So area cancels out, and we have just this expression left, that is just the current divided by epsilon naught. So in other words, the physical current that appears in Ampere's law on the side of the capacitor where the wire connects to it, that physical current is exactly the same in magnitude as epsilon naught d phi electric by dt. And so the time derivative of the electric flux times the constant of proportionality gives us that current, measured in amps, just like the current of charge flowing in the wire. And so we can now add this term that is called the displacement current, because it happens due to the displaced charges. So the displacement current being added to Ampere's law, that we shall now call the Ampere-Maxwell law. Adding that displacement current fixes Ampere's law. It doesn't invalidate how we used Ampere's law before. In all the previous situations where we applied it, if you think back, there was never a changing electric field that would have messed up our considerations. But now when we think about the capacitor, we can add that displacement current and make Ampere's law work for all situations. And a nice bonus along the side, we have kind of restored a little bit of the symmetry between Faraday's law and Ampere's law, where there was a time derivative of the magnetic flux in Faraday's law. We now have a time derivative of the electric flux in Ampere's law, Ampere-Maxwell's law. And so the equation means that a magnetic field can be created not just by a current, not just by an electric current, but also by a changing electric field. And so now we have all the necessary ingredients to state that a changing magnetic field is causing an induced electric field, and we can do that, for example, by increasing the current in a solenoid, and also vice versa, an increasing electric field causes an induced magnetic field. And note the direction of each of these. For each of these we can apply the right-hand rule and you can figure out the direction, right? We've done that with the right-hand rule, which way does the current go, which way does the field point, and then which way is the induced electric field, so that it causes a back EMF, right? And here, well, we've used the right-hand rule for the magnetic field around the wire, and similarly the orientation of the magnetic field here, just the right-hand rule in the same way applies. And if we turn this to look at the side view, it's going clockwise here for the induced magnetic field. So we have that symmetry. So let's review once more all four of Maxwell's equations. Yes, there's a difference between the electric and magnetic case for Gauss's law, but it's just because we don't have any magnetic charges, it's got to be zero here. There's also a difference between Faraday's and Ampere-Maxwell's law. We have the rate of change of the flux, magnetic and electric respectively. For Ampere's law we also have the physical current, but a current is moving charges, and so again, if we don't have any charges to move, then there can't be an equivalent term in Faraday's law, right? So we have a high degree of symmetry here between the electric and magnetic equations, broken only by the fact that there are free electric charges but not free magnetic charges. So this set of four equations is collectively referred to as Maxwell's equations, and you may feel like that's taking credit away from Gauss, Faraday and Ampere, but I think it's well justified by just how useful Maxwell's equations are with this symmetry, and how Maxwell derived electromagnetic waves from that. And all of electricity and magnetism really is described by these four equations and just the Lorentz force law added to it. the force a charge experiences in a region of space filled by an electric and magnetic field is given by the charge times the electric field plus the charge times its velocity cross the magnetic field. And so we have 5 equations describing electricity and magnetism, or electromagnetism as we now should call it. And really all of classical physics comes down to just a total of 11 equations. All of physics 1, all of mechanics is just Newton's first, second and third law about inertial reference frames, and an object in motion likes to stay in a constant uniform motion. F equals ma. For the second law, forces cause a net force causes an acceleration, and action equals reaction. And the universal law of gravity that explains both the apple falling from the tree and the moon held in orbit around the Earth. And then the only other thing we need to add to that for all of classical physics is the first and second law of thermodynamics, energy conservation, and the irreversibility of some processes. Disorder increases in the universe. I can convert, for example, electrical energy into heat, but I cannot convert all of heat energy into electrical energy. That whole business with entropy. So really just very few fundamental equations. Your formula sheet, of course, is going to contain many more equations than just these 11, but everything else on your formula sheet isn't as fundamental as this. It should relate back to these equations. The magnetic field inside the solenoid, we can easily find it by applying Ampere-Maxwell's law. The electric field inside the capacitor, we found that from Gauss's law. It's just an application of Gauss's law. Anything else, in physics 1 we discussed fluid dynamics, Bernoulli's equation. Well, it's really just a statement of energy conservation along a streamline of fluid flow, gas or liquid, right? And so all the other equations we've discussed really are just applications of these very few fundamental principles. And so that is the success of classical mechanics to unify so many different phenomena into very few equations. And Maxwell did that for electricity and magnetism. The refrigerator magnet sticking to the refrigerator and the compass needle aligning in an Earth's magnetic field don't appear to have a lot to do with lightning strike in a thunderstorm, or you getting zapped on a door handle if you walk across a very dry carpet. And yet they are just all phenomena of electromagnetism. So let's go through the 5 laws of electromagnetism again, and we've seen the equations, but let's restate these in words. And so Gauss's law says that charged particles create an electric field. Charged particles are the sources of electric fields. Faraday's law adds to that electric fields can also be generated or created or induced by changing magnetic fields. Gauss's law for magnetism says, well, there are no isolated magnetic poles. Ampere-Maxwell's law then says currents create magnetic fields, and the second half adds that also changing electric fields create magnetic fields as well. And then Lorentz law says electric charges experience a force in a region of space filled by electric and magnetic fields based on that electric field and the magnetic field if the charge is moving. So I challenge you to look at the equations and see if you can describe each one in terms like this, and look at these statements and see if you can write down the equation that goes with it. That way you really understand what each equation means and how to apply it. So that's the big success of unifying electricity and magnetism, and we'll next look at how Maxwell then used Maxwell's equations in empty space to derive electromagnetic waves, and those were then quickly found as well, of course. Alright, so that's it for this video. See you soon with the next one.